Hi, everyone. So I made an obvious gaffe. Obviously, Balmer's work was not in 1985. It was in 1885. I hope you caught that, and I will put a little footnote below the video. Well, anyway, that's silly. So we obviously don't have time to discuss modern theory of the hydrogen atom, but I'm just going to list some highlights. Highlights of the quantum mechanical treatment of the hydrogen atom. As always, well, okay, so first of all, the wave function will be a function of radio. We're going to work in three, yeah, so we're going to work in 3 dimensions. We do work in 3 dimensions. And in 3 dimensions, because the problem possesses spherical symmetry, potential energy is only a function of radius. As you go around any circle at a constant radius, potential energy does not change. So the potential energy is spherically symmetric. For this reason, it's common to work not in Cartesian coordinates, but in spherical coordinates. So in spherical coordinates, a point is labeled by not x, y, and z, but r, theta, and phi. So this is radius r. This is called azimuthal angle phi. And this is called polar angle theta. Okay, so this is spherical coordinates. And so the wave function, the full wave function, will be a function of r, theta, and phi. And it's also a function of time. As usual, we separate variables. Separate spatial. So seek, we're going to seek a variable separable solution. That psi is a lowercase psi, it's a function of spatial coordinates. And the other function of time, we plug the things into the full Schrodinger's equation. We're separated into the time independent and the time dependent. And the time independent part, the time independent Schrodinger's equation that's satisfied by the lowercase psi, and the temporal part. So this is going to be the solution is all going to be given like that, where psi satisfies time-independent Schrodinger's equation. And in 3D, it reads the following. Okay. I'm not showing the fact that psi is a function of r, theta, and phi. I don't always have to remind myself what its independent variables are. This is called the Laplace operator, Laplacian. Hopefully, you remember something from your 3D calculus. In Cartesian coords, this would be plus partial squared psi, partial y squared plus partial squared psi, partial z squared. In spherical coordinates, it's a mess. It's very complicated. So I will spare you that. So you would write down Laplacian in spherical coordinates, and this would involve a bunch of derivatives with respect to r, theta, and phi. Well, so far so good. But remember, we also have boundary conditions. Very important, because remember, it's the boundary conditions that lead to discretization, quantization. Discretization. Well, one of them is integrability or normalizability, rather, normalizability. In other words, the wave function has to go to zero fast enough as r goes to infinity in order for it to be integrable. It also cannot contain non-integrable singularities. So in other words, psi r by dv, this is volume, has to be 1. So it has to be integrable. But also periodic boundary conditions in theta and phi. This is new. So what this says is, as you go around any circle at a constant radius, you can go around as a azimuthal circle in the xy plane, or any circle. The solution has to smoothly connect with itself. You cannot have discontinuities. You cannot follow a circle and arrive to a different value of the solution. Now, the way the time-independent Schrodinger equation is solved by further separation into function of radius, function of the polar angle, and the function of the azimuthal angle. Your textbook does this. The product of these guys is often labeled by a function called big Y. So psi of these 3 coordinates is a product or function that depends only on the radius, and a function that depends on angle and on the angles. These are called spherical. Well, it's okay, it doesn't matter. But boundary conditions lead to this discrete set of solutions. Yesterday, we discussed the concept of quantum numbers. Quantum numbers are integers that enumerate discrete solutions. For particle in 3D box, for 3D rectangular box, there were 3 integers, nx, ny, and nz. And when we did the separation of variables, we saw that we could enumerate each well-defined energy state by a set of those 3 integers, nx, and y, and nz. For this problem, there exist 3 quantum numbers. They're always labeled n. This is called principal quantum number. L, this is called angular momentum quantum number. And M, this is called magnetic quantum number. I will just state the rules for you. That n can be 1, or 2, or 3, and so on. L can go between 0, 1, 2, up to n-1. And the magnetic quantum number depends on the L. So often they put a subscript. It can go from -L all the way to +L. It turns out that for hydrogen atom only, energies depend only on the principal quantum number. And we already saw them. We already saw that formula. Let me just reproduce it here. So you see there's a whole set of L and M's that can correspond to the same N. For example, when N equals 2, L can be either 0 or 1. And M can go all the way from, it can be -1, 0, 1, or 0, if L is 0. So there's a lot of degeneracy. There's a lot of degeneracy. You can have the same energy. You can have multiple states, multiple wave functions that all have the same energy. So there's a lot of degeneracy. Part of it has to do with the fact that the problem is very symmetrical. We discussed that more symmetrical problems have more degeneracy. Part of it is also an accidental degeneracy. It turns out that the wave function that depends on these three quantum numbers, the radial part of the wave function actually depends on N and L, but the energies do not. So that's why I said it's not just a degeneracy due to symmetry, it's also partly an accidental degeneracy. And the Y's, they depend only on L and N. Now we discussed that there are two conserved quantities. Even in classical physics, there are two conserved quantities, energy and angular momentum. In quantum mechanics, they're not only conserved, but they're also quantized. So we see that energy is quantized. It takes on only discrete values. It turns out that angular momentum is also quantized. And by the way, these functions, they're very complicated. They're not simple sines and cosines. There's some complicated functions. And there's no point in telling you what they are. You can look them up in your textbook. You have a few examples. I will come back to the discussion of wave function in a second. But first of all, angular momentum is quantized in the following way. First, the magnitude of angular momentum is quantized, and the values that it can take on is given by the following formula. It's not the same as the Bohr's idea that it's n times h bar. The magnitude is given by the following formula. So if L is 0, if little l is 0, the magnitude of the angular momentum is just h bar. If little l is 1, the magnitude of the angular momentum is square root of 2 times h bar. If little l is 2, under the radical you have 2 times 3, that's 6. Then the magnitude of angular momentum is root 6 h bar. But not only is the magnitude of angular momentum quantized, but it's also z component is quantized. And that's where the ML comes in. This looks more like a Bohr's idea. Now you might say, like, what's the z-axis? You just told me that the problem is spherically symmetric. It turns out that in order to measure angular momentum, you have to introduce an axis. You cannot measure angular momentum vector without actually breaking a symmetry and introducing some axis. Whenever you measure the angular momentum, the component of the angular momentum along that axis will be quantized. And so often they depict that as angular momentum lies on a series of cones. Right, so yeah, well, so something like that. It lies on a series of cones. It's just a mnemonic device. Don't worry if you don't understand it. This just says that, well, the angular momentum can take on only certain magnitudes. The angular momentum vector cannot only take on certain magnitudes. And its z component can also take on only certain values. So you have these three quantum numbers that enumerate possible set of wave functions and possible energies. So you have a discrete set of solutions, and ultimately discreteness is necessitated by applying boundary conditions like in all the other problems that we've seen so far. I told you that these wave functions are quite complicated. And so I think it would be best if I just show you pictures of particle probability density, psi star psi, or yeah, psi star psi, for several low-lying values of L, N, L, and M. So let me pause. So this is a picture from your textbook. As always, square of the magnitude of the wave function is the probability density. Now it turns out that the reason they write it like this, you might say, well, where's the phi dependence? It turns out that phi, the big phi, is just a complex exponential, so its magnitude is 1. And so the radial probability density depends only on the radius and a polar angle. So when an electron is in its lowest possible state, the ground state, principal quantum number 1, and the other two are 0, its probability density is strictly symmetric. It's actually largest at the nucleus. So this is a zero angular momentum state, completely zero angular momentum. You can have a zero angular momentum state, but the first excited level, energy-wise, and the probability density for an electron is a little bit more spread out. So this way of visualizing a function in 3 dimensions by its shading, where the shading is largest, the value of the function is largest. It's useful in describing functions of 3 variables. So here's a 3, 0, 0 state. So this is a state with 0 angular momentum and second excited state in terms of the principal quantum number. So here n equals 3, second excited state. And you see the higher the state, the more nodal surfaces it has. So the most low-lying grounds, the most low-lying state has no nodal surfaces. The wave function just goes to 0 as r goes to infinity. But this one has 2 nodal shells, 2 nodal spheres. Here is the state yeah, so I forgot to tell you, historically, the state with a little l equals 1 is called S. The state with angular momentum, angular momentum quantum number, little l equals 2, is called P. So this is a state where principal quantum number is 2, but angular momentum is 0, so that's 2s. And here are the 3 states with angular momentum little l being 1, and the m can be either 0 or plus or minus 1. Don't worry about it. This is just an excursion. It's just an exposition. I understand that you will not have time to digest this material. I'm just leading you through a discussion of what the electron density in these various states might look like. So the more excited the state, the more complicated is the pattern generally. So here's the state with n equals 3, and for example, little l equals 2. This is called a D state, SPD, little l equals 2. And then you can have m being 0, or plus or minus 1, or plus or minus 2. And so electron densities take on more and more complicated forms, generally, as you're looking at more and more excited states. So this says that, for example, in this particular state, described by these 3 quantum numbers, principal number 3, little l equals 1, and m equals 0, it says that if you were trying to measure the position of the electron, you're most likely to find it in the regions of darkest shading. You're never going to find it along this nodal plane. And then what's more obvious is you're not very likely to find it very far away. That makes sense. As an atom, as an electron becomes more and more excited, generally the region of, generally the probability of finding an electron further and further away from the nucleus grows. So you can see, you can compare this state versus this state. Probability density is more spread out, but it must always wane down to 0 as you go far enough from the nucleus. So this is just an excursion. Don't worry about it. It's just to connect the math with pictures. We are doing quantum mechanics like we have been in the last month. Well, we've been doing it for more than a month, but we've been doing real quantum mechanics for the last month. And so the same themes recur. The boundary conditions that enforce quantization. In one dimension, there's only one quantum number, the one that enumerates all the states and energies. In 3 dimensions, there's a larger set of quantum numbers. For hydrogen atom, there are 3. There's a triplet of quantum numbers. One is called the principal quantum number. For hydrogen atom, energy depends only on that one. For other atoms, energy also depends on the state of the angular momentum. And there are 2 other quantum numbers that describe the state of the angular momentum. Angular momentum is quantized, and one quantum number tells you the magnitude of the angular momentum vector, and the other one tells you the z component of the angular momentum vector. I think that's all I want to say about the hydrogen atom and the modern treatment of hydrogen atom. Of course, we could spend multiple lectures or multiple weeks, if you wish, discussing hydrogen atom. We don't have time for that, so this was the minimal presentation that I think is fair. Okay, so on this note, I want to thank you for bearing with me together through this lecture. This was very challenging for both of us. I tried to do my due diligence at refilming as many lectures as I possibly could. I spent countless hours preparing new homework exercises for you and new solutions. I tried to go out of my way to make sure that you're able to navigate this really challenging class in this really challenging environment. So of course, we'll make mistakes, and things that I try for the first time is most likely to be plagued by mistakes. Some of the things I did try for the first time this quarter, like the way I decided to handle the finals, but we learn from these mistakes. So thank you. Thank you for your attention. And I will see some of you in other classes. All right. Thanks.